Hello, thanks for stopping by the poster. I'll be telling you about Levy in active turbulence. So, what's the system that we have? Basically, when you have a dense suspension of active entities like bacteria that can push and pull, they can give rise to collective flow patterns, as you see on the left, which can be fairly complex and very vortical, as you see in this colorful picture of the vorticity. What's interesting is that you can describe such a system using a generalized Navier-Stokes equation, which is given here below. I won't focus too much on it. The most important thing to note here is that for this talk is that there's a parameter called alpha, which is the activity of the system. And if you make alpha very negative, you start injecting a lot of energy into the flow. And that gives rise to all kinds of flow patterns, which can be turbulent. So for instance, here you see a snapshot of an active turbulence simulation with a lot of vortices throughout the domain. And if you see this kind of a flow with a lot of tracers and you measure this quantity, which is the mean square displacement, then you get a very typical ballistic to diffusive transition. So your mean square goes from t square to t. Now all of this is all right, except that some experiments have shown that this mean square displacement can go anomalously in time. So it can have a exponent higher than the diffusive scaling of t. So we wondered why we didn't see this in simulation so far, and how can we sort of can we get this behavior in simulations? So for that we perform simulations with increasing activity. So from left to right is from left to right is increasing activity, and what you see is that the nature of the flow begins to change. So in the middle you have a lot of vortices that are diffused, move around, and on the right you get also large vortices and also streak-like patterns in the flow. So there is certainly a change in the Eulerian nature of the flow at increasing activity. The question is, what does this do to tracers? So for that we then see this flow with tracers. Here you see a sort of a blob of tracers diffusing with the flow, and in the middle you see really diffusive motion. The tracers are moved around by the vortices that become very visible. Whereas on the right, which is extremely active turbulence, what you see is that there's a sort of a mixture of the kind of motion that these tracers have. So you get vortices as well as material lines that just translate along without distorting too much. So there's also a change in the Lagrangian nature of these flows. So how can we quantify this? So then we look at the mean square displacement for different activities. And indeed, as you see, that when the activity increases, then your mean square displacement, rather than going to diffusive scaling of t, it goes to a anomalous scaling of t to the fourth hertz. So indeed, these flows can have anomalous diffusion. The question is, does this come from Levy-Vox? And for that, we need to look at the statistics of trajectories. So here's one sample trajectory which has been segmented into different walking lengths. And this is basically the points give you the turns, and between the points is one step, as it's called. And between two turns, you also have a waiting time. So then we look at the distribution of waiting times, and you can do this for different thresholds of the turning angles. And what you see is that the waiting time tau, it follows a power law distribution. And most importantly, it has an exponent 8 thirds, which together with the 4 thirds from the anomalous diffusion is consistent with the constraint for Levy-Vox, which is given here below, that your Z plus gamma is equal to 4. This, together with the fact that there's a more or less constant velocity in the system, shown here by the joint distribution of the step lengths d and the waiting times tau, which is more or less linear, we can conclude that the system actually has Levy-Vox that lead to anomalous diffusion, and that really sets your active turbulence apart from inertial, because all of these things do not happen in inertial turbulence. So what's next? Well, the question is that the Eulerian features that I mentioned, are they related to persistent motion or Levy-Vox? Because if you look at instantaneous streamlines, then indeed your streamlines, they seem to be very straight in the streak regions. And other Lagrangian measures, for instance, pair dispersion, you also have the first passage problem. How do they change for active turbulence? And we've actually quantified all these things. And if you're interested, please visit the poster by Rahul Singh. It's called Lagrangian manifestation of active turbulence anomalies. And with this, we are trying to understand the question whether active turbulence is like turbulence, because on the one hand you have these similarities like intermittency, tails of vorticity, power law distribution of energy, but then you have Lagrangian features that are anomalous. So with that, I'd like to end. Here's a reference for the poster. This work was recently published and it was done together with Rahul, Martin, and Shumriddhi. And I'll be very happy to take your questions. And if you want to know more, please write to me. Here's my email. And thanks a lot for stopping by the poster.